Now you have set up the complete TaPaSCo on your machine, and I'm going to talk a bit about the first kind of design entry that TaPaSCo supports, which is the HLS flow. So the HLS flow is especially if you want to start from C or C++ kernels to build a system. And so we have this standalone C and C++ kernels that you wrote yourself, and the first thing you need to do to get it into TaPaSCo is to call the high-level synthesis, which is going through TaPaSCo. So we have abstracted away the complicated commands of the vendors. Instead, you have a pretty simple command, and you will end up with one of these ipexec cores. So ipexec, as Jaco already told you, is the format that especially Xilinx is using to package cores. It's basically a zip format with some XML information in it, but you don't need to know the details of ipexec to use TaPaSCo. Yeah, so we'll have a really simple HLS example. In this case, that's one of the ones you can find in your kernel directory in the TaPaSCo directory. So this is summing up the values of an array. So it's a loop iterating over all the values in the set much values in the array and summing them up into a variable, returning that variable. So that's basic C or C++ code. You can even tell from that example. And the only requirement for TaPaSCo to work with that code is that the code needs to conform with the requirements of the HLS tool that you want to use. In our case, we want to use the Vivado HLS tool, so it needs to conform to the requirements of Vivado HLS, which are documented in their user guide. So TaPaSCo doesn't add any requirements to your HLS code other than those given by Xilinx. The second thing you need to run a kernel through TaPaSCo is this kernel description in JSON format. It's pretty simple. You have a name, you can choose any arbitrary name. Probably you should not have a space in there and some special characters, but other than that, you can call it whatever you like. You have to specify the top function. So if you take a look here, the function that our kernel is the top level function of our kernel is called ArraySum, so we put that here. You can give a version. That's up to your choice. You can call it 1.0, you can call it, I don't know, 8.0, whatever you want. This ID is going to become relevant later on. So every processing element in TaPaSCo has an ID, which is used to identify it if you want to use it from the software interface. That's just a number. Hint, you should not use the number 0 here, because the 0 element is an empty slot in TaPaSCo, but any other integer number will work here. You need to give the files that the kernel is built from. So in our example, we have just a single function that is in the file array.sum.c. These names, they don't need to match, but in our case they do. Another thing that TaPaSCo supports is the co-simulation of your HLS kernel. So if you specify a file here containing a test bench, and if you want to look at this test bench, just check out the kernel folder in TaPaSCo. It's basically calling this ArraySum function with different values and checking if the result is correct. And this is going to enable the Vivado HLS co-simulation. So Vivado HLS will build a hardware accelerator from your C code, and using this test bench in this test bench file is going to test if the generated HLS core is doing the same thing as expected. Another important part is the arguments here. If you look at our function again, we have a single parameter to this function, which is the array called R. So we put the name of the parameter here, and there's basically two kinds how you can pass a parameter to a TaPaSCo core. One is by reference, as in this case, which means that there will be memory allocated in the DRAM or in some other memory on the FPGA, and TaPaSCo is going to give the function or the core a pointer to that memory. The other option is by value. So if you have a by value parameter, TaPaSCo is just going to pass the value that you give it. So if you give it 42, your kernel will get 42. So that's all you need to specify to run a kernel through TaPaSCo. That's just giving TaPaSCo some hints on what your kernel does and how it should be used. It's standard JSON, nothing special to that. So we now have everything we need to run a kernel through TaPaSCo, so we can call the TaPaSCo HLS command. And you see the invocation down here. We just use the TaPaSCo command line tool. We give it a command, in this case HLS, to say it execute high-level synthesis, and we give it the name of the kernel, which matches the name we specified up here. So that's all you need to run high-level synthesis for this array sum example. So let's get our hands dirty. So we have done the first steps already together with me. So it's now time that you run free and produce the first errors, so to say. So you can check out the TaPaSCo manual page first, just to get to know the command a bit better. And then for each command or for different topics, TaPaSCo has so-called help topics. So if you run TaPaSCo-H, you get the help. And if you, in this case, pass a special command to it, it will give you detailed information on that command. So once you have done these two steps and got a bit familiar, we have provided a Sobel kernel in the Docker image under this path. I will leave this slide up for you so you can always see the path. So you should complete the kernel JSON in that directory. There's already some skeleton given, but you have to put in the values where there's a to-do. And you should use the ID 42 for that. If you need information about the kernel JSON and what you should put there, just check out the TaPaSCo home/kernel directory. And then the final thing you should do is run TaPaSCo HLS with that command. So try it out. In case you stumble upon any problems, raise your hand. We will stop by and help you. And yeah, get to know TaPaSCo HLS. So how far is everybody? Anybody still struggling really hard, or most of you got it right and deleted the quotes around the ID and all the nasty stuff? Okay, perfect. So let me show you how we would do that task. So our setup is basically the same as yours. So we also got this HLS in here with the Sobel CPP. So that's actually computing a Sobel filter for an image of the sizes width and height. Probably all of you know this Sobel filter is for edge detection in images. Rather simple one. And the three things you have to remember if you want to complete your kernel JSON is that the function is called Sobel in this example, and you have two parameters called input and output. So that's basically all you need to remember from the Sobel CPP. So our kernel JSON is just as empty as yours, but just as in a good cooking show, I have prepared something here. Let's go through it quite fast. We have the kernel. We have called it Sobel. You should do the same because our Vivado HLS is expecting that name. But apart from the tutorial, you could call it any way you want. The Sobel top function. I'm getting bitter. Okay, let me quickly. So we get it bigger for you here. So the top function is this Sobel up here. We have given it a version 1.0. That doesn't really matter in our case here. The ID 42 important. It's without the quotes because we inspect an integer here and not a string. We have the file is Sobel CPP, just as it's called in the directory, and we have our two arguments, input and output, and they are both arrays, so we want to pass pointers to some memory. So we have the passing by reference for both cases. So, yeah. Yeah, yeah, I mean it's pretty nice to say it's not ideal. There's other words that come to my mind. We're right now looking into that, how we can improve it. The problem right now is that Jens, who gave the talk yesterday, if you saw it, that's a hand-built, handcrafted JSON parser, and we need to get rid of that, and that will take us a day or two. Yeah, that's with play JSON, and if he expecting an int there and he doesn't get an int but a string, it will just fail, and there's no he doesn't encode a reason why it failed, and we have to get rid of that. But that's on our list, our to-do list, because you're absolutely right, that's far from ideal right now. Okay. Yeah, we can do that, sure. Okay, thank you. Okay, next thing we need to do is to get to run the HLS for our kernel. So the first thing we have to remember is that we're currently not where TaPaSCo is. So if you look where your TaPaSCo home is, it's not the folder where we are currently at. So we need to tell TaPaSCo where to find the HLS kernel we want to run. We are going to use the verbal flag, so you're going to see a bit more in a minute. And for the telling TaPaSCo where your kernels are located, we have this kernel dir option, which you can find with TaPaSCo -h. I'm just going to tell them that it's here. And we're still going to tell them we want to do HLS now, and we want to do it for this kernel called Sobel. And just to get it a bit quicker, we are limiting ourselves to a single platform, so we're using the -p option that you have on each command in TaPaSCo, which is just telling TaPaSCo to use only the platform we specify, so in this case the VC709. That will make things a lot quicker if you probably will only have a few boards, not every board that TaPaSCo supports. And if you're doing HLS or composing bit streams, you do not want to do that for all of the platforms TaPaSCo supports. If you're really in a hurry one day, there's another option you should know about. That's the -skip evaluation. The evaluation of TaPaSCo is basically it's doing an out of context synthesis of your processing element to get to know the basic frequency of the element and how much resources it probably needs, and all this information is relevant for the design space exploration. But if you're not running design space exploration with that core, you can use the skip evaluation flag to not run this out of context synthesis, which is taking like 20-30 minutes depending on platform and kernel. So that's a secret hint by the TaPaSCo developers for you. We're going to let this one off because our Python script is fast anyway, so just hit enter and hope that you didn't fail. That looks good. So we started in verbose mode, so we're going to get a lot of output now in a second or two, because the realistic feeling of using Vivado and Vivado HLS is only there if you wait for everything for forever and longer. but I was able to convince Carsten that Vivado shouldn't fail on every second occurrence, so you won't have Vivado errors today. You can get back to that tomorrow. Okay, we're already done. One interesting information is down here. When you're doing we just ran the evaluation, so TaPaSCo did an out-of-context synthesis for your core and tried to find out its basic frequency, so that's the starting point of design space exploration. It's aiming to synthesize your processing element at an operation frequency of 1 gigahertz, which is not realistic on most FPGA devices today, but it gives us an upper bound where to start design space exploration. So we have a worst negative slag of something close to 1.7 nanoseconds, combined with the basic slag of for 1 gigahertz, we get a period of 2.6 nanoseconds, which is equivalent to a frequency of 370 something megahertz. So that's the interesting information in this case. So if you would run design space exploration for that kernel, TaPaSCo would try to start with an operating frequency of this 373 megahertz. So now our kernel, we have successfully run HLS for our kernel. We can check that if you want to. You can have a look in TaPaSCo home directory, in core. There's all the cores currently available because we've only run HLS for this single Sobel kernel. There's only the Sobel in there. And if you have a look into Sobel, there's the architecture. So currently the base architecture is this AXI4 based one. And we synthesized for the platform VC709. So we only have that platform here available. And if you look into there, there's some logs, and there's this IP core where you can find the zip, which is basically the IP exec that we just created with our HLS command. So any further questions regarding HLS so far? Yes? It's by value and by reference. That's the two options you have there. Sorry? Not right now. Because our base architecture is this random access memory thing, so we don't have stream support for the HLS kernels right now. Okay. So if there's not any more questions on HLS, I'm going to pass on the microphone. Oh, sorry. Yeah, sure. Yes. It's probably because putting arguments about something in JSON means you're building an object, and probably was able to infer that object. But that's my guess right now. So yeah. Yes. Yeah, because we have this fake Vivado HLS. We only have logs for the VC709 in that hidden folder that we copy over. If you would run it with the real TaPaSCo and that's real TaPaSCo, but with the real Vivado HLS, that would work. So that's only a limitation of our tutorial today, because we don't want to blow up the container. Okay.